So basically we are doing the contour integrals, and now we have to do one more question. Let me rewrite that question once again properly. Then we will also solve that question. Contour integrals. The question is something like this. So a complex function is already given to us. Like in the question, we have been given a, like we have to evaluate this integration of the complex function, which is 2x plus iy plus 1 dz. This we have to evaluate, and the limit is 1 minus I. Upper limit is 2 plus I. This we have to do. Okay. So you can get a question like this, wherein only this integral will be given and nothing else will be given. And from this integral, we can see that this we have to find the contour, the interval of the contour is given, the arc, that is the 1 minus I to 2 plus I. So the contour is defined over that point, and we have to first find the equation of the contour, then integrate that. The similar way which we used to do the earlier problems. The first goal is to find the equation of that arc, the contour. Then the integration of that we will do. So whatever information is given to us, based on that, we have to work. So the limits which is given to us, we can break these limits into the points, because these two numbers are complex numbers. I can write them like this. Somewhere here I will write it. I will say that, okay, z1, which is the lower limit, which is a complex number, that is I minus 1, and z2, that is 2 plus I. So ultimately I will get 2 points, like
Yes, sir.
1 comma minus 1 and 2 comma 1. Now what I can do, I can visualize this.
-1, 2, right?
No, so the
-1, 1.
no. So see, whatever I have written, that is right. So the lower limit is 1 minus I, and upper limit is 2 plus I. So 1 is the real part and minus 1 is the imaginary part. So 1 comma minus and 2 comma 1. Okay, so this is how I can write it. Because there is a typo in the question. In the question, in the lower integral, it is written I minus 1, but exactly it is 1 minus I. Okay. So whatever question I have written, that's the right question. And this is the point we will get for that question. Now we will plot it. These 2 points in the complex plane, we can plot it. Let us do that. This is the real part. This is the imaginary part. Now I can try something like this. 1 comma minus 1. It will be somewhere here. X is 1 and y is minus 1. And x is 2 and y is 1. Something. Now I can join it. I can join these two to get a straight line. So this is the straight line passing through that two. Let me write that points here. So this is the 2 comma 1. And this is 1 comma. Now this is the contour. Because contour is an arc, so this straight line can be an arc, and we have to do the line integral of this line for this function. Let us try to do this. So now we have visualized the contour. Now our goal is to find the equation of the contour, because now the contour is a straight line and I know how to find the equation of a straight line. Let us do that. So I will let us do some basic revision. We know that for any 2 points, x1, x2, y1, y2. Sorry, x1, y1, x2, y2. For any 2 points in the coordinate space, if we know the 2 point, we can get the equation of straight line. The equation of straight line will be something like this. Equation of straight line, we know it will be y minus y1, y minus y1 is equal to the slope is y2 minus y1 upon x2 minus x1. That is the slope. And x minus x. This is the equation of straight line when we know the 2 points, x minus x. Now we can apply the same concept for the 2 points which we have, because we have a straight line for the 2 points. So the equation we will get here, it will be y minus y1 is y1, or yeah. So what I am assuming is 2 comma 1. I can write it here for clarity. This is x1 comma y1, and this is x2 comma y. So y minus 1 will be equal to y2 minus y1 minus 1 upon 1 minus 2. And then x
So we are
minus
doing this for the limits.
no, we see ultimately in the contour integral, the first step is to find the equation of the contour. So here the contour is the straight line, and we are finding the equation of the straight line. We know the 2 points. 2 points we got from the limits, and we know that these two points it is lying on a straight line. And if we know the 2 points, then we can know the equation of the straight line using the formula which we are discussing. X minus x1. That is 1. Okay. Now, if we can simplify this, after simplification, if, the simplification you will do, you will get an equation like y is equal to 2x minus. So this is the equation of the contour. And here I can say that dy, like dy by dx, so dy will be 2 dx. And one more important observation we have to make. Here, if I talk about x, x1 to x2, so like x is varying from 1 to 2. Here, x is varying because the point, if you look at now, x is varying from 1 to 2. Because this is the x, this is the 1, x is varying from 1.
So why did you say that?
Yeah,
Because
we,
in both the like 1 and 2 are there. That's so.
yeah, see, x is varying from 1 to 2 in the interval, and hence we can say that x is varying from 1 based on the interval given. It's given. Now we are all set for the integration. The integration which we want to do, let us write it. Like ultimately, we have to find this. The one I'm writing. This is the question. Integrate this function with 2x plus iy plus 1. This is what we have to calculate. And limits is 1 minus I2, 2 plus. This is what we have to calculate. And whatever contour equations we have got, now let us see how we will use that to solve this integration. Okay. So see, one very important analysis we have to do. We know that general equation of any complex like z is, let us suppose x plus iy, then dz will be dx plus I dy. So instead of dz, I can write dx plus I dy. Now we can do this. How we will be doing this, I will show you. So see, this we can keep it as it is for now. 2 plus I. The inner function, this for now we can keep it as it is. For now. Instead of dz, I can write dx plus I dy.
X plus I dy.
Now what I can do, I can like multiply it, like simplify it. So when I will do that, it will become something like this. Integration of 1 minus I, 2 plus I. And when I multiply it and I bring the real part together and imaginary part together, then I will get something like this. Like we can do it here itself. See, 2x dx or the 2x dx just 2x dx. So dx I will be multiplying with all the terms. No? That is what I will do. Plus I by dx. Plus dx itself. Then plus 2x I dy.
Hmm.
2x I dy. Then plus I square by dy. And I square, what you can write? I square is minus 1.
Minus
Minus 1 I square y minus y. And what is the last term? Last term is I dy plus,
तो y dy कैसे हुआ?
yeah, I will. See, the idea is that if you multiply this and this, I square will become minus 1 and y is already there. So minus y it will become.
Oh,
Okay. Now what I can do is I can bring the real part together and imaginary part together. I can bring the real part together. I can 1 minus I, 2 plus I. So when I bring the real part together, I have like 2x dx. Plus dx.
Minus y dy.
Minus y dy. Okay. This is clear.
Yes, sir.
So this I can write plus I. Imaginary part I can bring it together. So y dx. Imaginary part into y dx. Then 2x dy. dy. Then
I
dy. Now what I will be doing
Y
is
dy
that
also, sir.
no,
The
y
second
dy
one.
is the real part. That is here.
No, sir. Second one. I dy. Oh,
Yeah,
that
that
X.
yeah, that we have taken care of. So this is there. So we have included all the terms. Now what I will do, now instead of dy, I can write it 2 dx. Wherever dy is there, I can write it 2 dx. So this, the integral, we will convert it only into the dx form. We will get rid of the dy. And hence, since we are analyzing the dx, we have to consider the variation of x, and x varies from 1 to 2. So limit we can convert it to 1 to 2, and dy we can write it 2 dx. And why we can do that? Because we have just like proved this. So 2y is equal to 2 dx. So instead of dy, I can write 2 dx. And when I am doing that, in the integral, the limit I will set from 1 to 2. So let us do that. So now what I'm trying to do is I'm simplifying the integral in such a way that limit is from 1 to 2. And wherever I have dy, I will convert it into 2 dx. So 2x plus 1 minus 2y. The bracket I will have dx. Because here in the real part I have dy, I will convert it into dy is equal to 2 dx. So dx I can take outside, so I will get something. Similarly, iota. Here I have dy at 2 places. So it will become something like this. Y will be as it is. It will be 4x plus 2. Outside I will get dx. Okay. Now one more thing I have to do. Instead of y, I can write 2x minus 3. Because since this is a single integral with respect to x, I have to get rid of this y. I have to make this
So why
integral
not? We can write
2x minus 3. which the equation which we derived. Y is equal to 2x. That we will. I will write it here for reference. Y is equal to 2x. This is the equation of the contour. One, two, two. 2x plus 1 minus 2 into 2x minus 3. dx plus I 2x minus 3. This time, yeah, 2x minus 3 plus 4x plus dx. Okay. So wherever y was there, I replaced it with 2x minus 3. Now I can do some simplification. To get something like this.
That will be minus 2x plus 7 dx plus I 6x minus 1 dx.
Okay. So minus 4 plus 2. So minus 2. That is right. Minus 2x. And it is minus 6 plus 1. Okay. Minus minus it
7.
will be plus. Okay. 7 it will. That is right. So minus 2 plus 7 dx. Okay. And then I 6x minus dx. Now what I can do is that both the real term and imaginary term, I can integrate separately and put the limits to get the answer. So it will be minus 2 x square by 2 plus 7x.
7x.
The limit 1 2 plus iota 6 x square by 2 minus x with the limit 1 to 2. After putting the limits, like one more step we can write. So see this 2 I can cancel.
Yes.
So when I cancel it, here I will be having minus. So it will be minus x square plus 7x. And when I will put the limit, it will become minus 2 square plus 7 into 2 minus
Minus
plus
plus
2 plus 7. Plus. Similarly, here it will become I 3x square minus x. So 3 into 2 square minus 2 minus 3 minus 2. So final answer I can write it. So it will become -4 plus 14. That is +10. +10 and -5. So +5. Okay, so once again, yeah, +5 plus I, 4, 4 3s are 12. So it will become 10 minus 8. 5 plus 8. This is what. Okay. Okay. One mistake I did. Sorry. One correction. It will be 1. It will be 1.
I can't go till the I can't stop that. Oh, you want me to get into the shuttle with this bag? Oh, just see how much I can't try to lift it up. I have no clue why I can't lift it up. But yeah, it is easy. No, last time it was very light.
So it will be 10 minus 6, which is 4. It will be 4 plus 8. Now it's fine. This is the final. So this is how we solved this problem, this integration. Now let us do one more problem. So here we have been given a function like z plus 2 upon z. Dz. And here C is the semicircle. It's here capital C is the semicircle. That is z is equals to e to the power of 2 e to the power of I. 2 e to the power of I. And it's also given that the theta, it varies from 0 to pi. So this integral you have to do. So this is a complex integration which you have to solve. So it's a contour integral. So here the contour is a semicircle. Its equation is given. So half of the work is already done. Now, based on the intervals, you can get 2 points, plot it, visualize the contour, and solve the way we solved other problems. So what I want is that you take it as a assignment, like this particular question, you give it a try, and if you face any problem, let me know. Then we can discuss it. Okay. Like
Right
this.
now.
No, later on you do it. You do it on your own, and if you are facing difficulty, then I will help you to solve. The same way you can refer the other questions which we already discussed. Same way it will be solved. Here equation of the contour is given. Interval is given. Using the interval, you can visualize the contour. Limits you will get, and do proper substitution. Z you know, dz you can calculate. You can integrate it. You can give it a try. And one interesting thing I will share with you, like this, you have to make use of a property that I think you are already aware, that e to the power of I theta, it is cos theta plus I sin theta. Okay. So this will make the work easy.
So 1.
Yeah.
No. Yes.
Okay. So this topic is complete. Now we will look into the next topic. Next topic which we will be discussing, that is the Cauchy-Borsuk theorem. Let me write. So, first, let us understand this theorem. Like two theorems we will understand, and based on the results of those two theorems, we will solve some more interesting problems. Okay. So what is this theorem? Let us try to understand. So this theorem states that if a function fz is analytic at all the points interior to or on the simple contour, which is a closed curve, then the integration over that region is always zero. I will state it properly. Then you will get a feel of it. Like whatever we are trying to say, we will understand it. So this theorem, it states that I have a function fz. If a function, complex function, if a complex function fz, it is analytic, at all points. I have a function fz which is analytic at all points, interior to, at all points, interior to and on the surface, or and on a interior to and on a simple closed curve. Simple closed curve C. Then integral over that closed curve or the region. The region is the closed curve itself. The closed curve and the interior of that will be the region. So the integration of function fz dz will be equal to 0. So this is the idea. Now see, we are already aware that what is closed curve. Curve means any arc, like any curve, and if it is closed, it will be something like this. So it is for example a closed curve, and all the regions, yeah, all the points like the fz, it is analytic on all the points in this region and also on the curve itself. On the curve also, the points are analytic and also interior to this. So if we do a integration taking into consideration all the points inside this region and the points lying on the curve. So interestingly, that integration will always result into 0. And here, let me emphasize it. This is the boundary. Property. The points lying on the curve and interior to the curve. If we do the integration of a function over all these points, so that integration will be 0. So this is the Cauchy-Gaussian theorem. Now we can state it in one more way that I can state it here. In another way also we can state it. It says that if fz, the function, is analytic, if fz is analytic on some simply connected domain D on some simply connected domain capital D, then for every closed contour C within D integration of that contour fz dz will be equal to 0. The same thing we stated it in a different way. So here what we are saying is that let us suppose we have a connected domain. So connected domain is is a kind of a region. We have a region, and in that region, within that region, if I draw any random contour, closed contour. So let us suppose I have any random region. Let me forward. Any random region we can take. This is any random region. Now, if I draw any, like it is a connected domain. So the region which I have highlighted, it's a connected domain D. I can write D here. It is the D connected domain. Now, any random contour I can draw, closed contour. Let us do that. Any random contour I will draw, which is a closed one. So this is any random contour. Now the integration over this contour of for the function fz dz is the same thing we stated it in the another way. So this is the here. Now based on this theorem and one formula we should know that we will discuss like another result. Then we will use that to solve some interesting problem. So now we will be discussing Cauchy's integral formula, which is based on the theorem itself. Cauchy's integral formula. So let us see what this formula is about and how to use it. Application. That's important. To solve problems. Yeah. So let us suppose I have a function fz, a complex function I have fz, let fz, and let this function be analytic. Let fz be an analytic function. Let fz be an analytic function within and on a closed contour C, within and on closed contour C. Now let us suppose if z is equal to a be a particular point. If z is equal to a is any point within C, is any point within the contour. is any point within the contour C, then very important result we are I'm writing it. It's we have to use it. Very important formula. It is f of a. And what is a? A is any point within the contour. So f of a we can get. What this f of a will be? This f of a will be 1 upon 2 pi I. 1 upon 2 pi I integration of C, integration of integration over the region, the integration over the contour C, and the function which is f of z upon z minus dz. So this is a very important formula. We have to remember it. So with this formula, we can see that how the value of the function at any point can be determined using the contour integral of that function divided by z minus. So this relation is very important for us. And we will solve some problems to see how to apply this. And one more very interesting thing you should know, that is whenever we are doing the contour integral, always we have to do it in a positive sense. Positive sense, like normally the anti-clockwise is taken as positive. So the integral should be in the positive sense. Very important. Integral is taken in the positive sense around the contour C. Integral is taken in the positive sense. Integral is taken in the positive sense around the contour C. Now let us look at some examples, how to apply this or how to use this. Then we will become familiar with this formula. I will write one example. Let us suppose we have to evaluate this integral z upon z minus 1, z minus 1, dz. Let us suppose we have to find this contour integral, and here the contour is given. The contour which is given is the C, that is the contour. It is a C is mod of z minus 2 is equal to 1 by 2. This is the contour, and we have to find the contour integral like this z upon z minus 1, z minus 2 dz. This we have to find. So contour, it defines the region. It defines the region of the points. And for that points, we have to find the integration. Like definite integral. It is a kind of a definite integral. So now what what we can do, first let us visualize the contour. So we are already aware of the fact that mod of x minus a is equal to r. It represents a circle with a as the center and r as the radius.
Radius.
R as the radius of the circle. So this notation we are aware of. So this is one of the way to represent a circle. Like this form represents a circle. So whatever is given to us, the contour, it is a circle with the center at point 2 on the real axis and the radius is 1/2. Now we can very easily visualize it. Now we can visualize the contour. Let us try that. So I am drawing the complex plane wherein I have the real axis and I have the imaginary axis. And let me draw some points. Now 2 is the center. This is the center and radius is 1/2, half. So the circle, it will be like 1.5 to 2.5. Circle will be from 1.5 to 2. And let me try to draw a small circle. Let me look at let me make it fit. So it is not a
So
perfect.
this big figure.
This is the contour. This circle which we are drawing is the contour. We are visualizing the contour based on the equation of the contour. The equation is given, C, capital C is the contour. It is given in the question. Mod of z minus 2 is equal to half. And we know that this equation represents a circle. And we got a circle. So we were able to visualize the contour. This point, it is 2.5. This point, cutting, it is 1. Okay. Till here, so it is clear to us. Now, one more thing we can do. Like whatever function is given to us, because here we have some singular points in the function. So let us deal with that. So now what I am trying to do is that whatever function is given to us, I will break it into the partial fractions. So this function, I can write it like 2 upon z minus 2 like after breaking it to the partial fraction, minus 1 upon z. This is what you after breaking it into the partial fraction. Okay, this is very clear. Now what else? Now here, definitely we have two critical points, we can say that 2 and 1, at which the function will not be analytic, something like that. So let us focus on these 2 points. Let us focus on these 2 points. I can say that at z is equal to. Now see, one very interesting observation you will see that z is equal to 1 is a point which is outside the contour. And we are not at all interested in that point, because see, we are integrating this function for the points which should be either on the contour or inside the contour. But z is equal to 1. It is a point which is outside the contour. So for this at z is equal to 1, I can write integration of the contour z upon z minus only this part, or z also, right? Just dz upon z. This part, it will become 0. See why it will, because see this integration, it is the sum of the points either on the contour or within the contour. Now this one is outside, so no need to include it in the sum integration. So it has to be 0, and I can give the reason why I am using it. Since z is equal to 1 is outside the circle. Outside capital C, like outside the contour. So this is also making sense. Now the next point, we can focus on it. At
So ये भी तो 0 ही होगा.
no. At 2, so it is inside the
ये भी तो
contour.
बाहर है ना.
No, why? 2 is inside, na? See, so circle is defined 1.5 to 2.5. So 2 will be inside the circle, no? 2 will be here. I believe. Yes. 2 will be here, isn't it? And it's inside the circle.
Yes, sir.
2 is inside the circle. So at 2, the point is inside the circle, and now we just have to find. So here we can say that integral is defined.
So
Integral is defined. Like we will calculate the integral, but
why?
at z is equal to integral is defined, now we can calculate the integral. It will not be 0.
Because it's in the range of the contour.
Yeah. Because it is range of the. Now we can do that. So ultimately, what we have done is that we have reduced, or we have simplified this problem. How we have simplified this problem? After all this analysis, we can say that we have to find this, which is the question. Now this I can reduce it to this.
So
Like
इसमें z minus 1 भी include होगा.
No, z minus that is what I am simplifying it. Z minus 1 now I am removing it because we have seen that will not at all that will play no role here. So ultimately I am interested in finding this z upon integration of like z upon z minus 2 dz. This is what I have to. Now always remember, whenever you have an integration wherein in the denominator you have the form z minus a, because then you directly apply this formula, Cauchy integral. Like you have to remember this formula. And see here, this integration, we can very easily see that it is having z up, like in the denominator z minus a form. So this formula I can use. And how I will make use of this formula? Let us see. According to this formula, what I can write is here a is 2. Here a is 2. Without what we have to calculate, I can write like this. F of 2.
सर हमने z इज इक्वल टू 1 में ये z क्यों नहीं इंक्लूड किया है जैसे यहाँ पे करा है z अपॉन में z minus 2.
No. So we have seen at z is equal to 1, the point is outside the circle. So this integration will become 0. So no need.
लेकिन ये तो सॉल्व करने के बाद पता चला है.
You have to first analyze it. First you have to do the first you have to visualize the contour and analyze it. After analysis, we can see there is a scope of simplification, and we simplified it. Question will be like this only. Question will be in such a way that whatever integration you have to do, that will be resembling with this form. So first we have to bring the integral into this form. And if you are not able to bring it, you have to figure out a way. Like there is some trick involved. And what is that trick? Some points may be outside the contour. Like in this example we saw, like z is equal to 1, it was outside the contour. So no z minus 1 in the denominator, this function 1 upon z minus 1, it will not at all influence this integration. So we can ignore it. So that is what we did. Now we are like relating this formula, like so a is 2, so z minus 2, 2 pi I, this is a constant, I have to write it as it is. Then this will become integral of c, that's a contour. Then f of z dz. Now here it is the same itself. Like this thing is the same, this integral which we have to calculate.
Yes, sir.
Z upon z minus 2. This is what we have to calculate. Now very smartly, what I can do is, now though I'm very close to the solution in such a way that I can write using this integration, like contour integral of this z upon z minus 2. dz. It is equal to 2 pi I multiplied by f of 2. And f of 2, how you will get f of 2? F of 2. Okay. So see, if we correlate this formula with the form, You can see here, I will write this. F of z is equal to z. The numerator. Let me highlight it. See, f of z is equal to z. Okay. Whatever is there in the numerator, that is the f of z. So according to this, what I can say? I can say that f of 2 will be 2. F of 2 will be 2. Even 2. So that is what. So f of 2 will be 2. So the final answer which you will get, it will be 4 pi I. So we were able to solve.
So
Or
we
you
didn't
can,
have to solve the integral here.
so we can say that this integral, it is 4 pi I. It is 4 pi.